Hi and welcome to this second video, and in this video we're going to look at nerve conduction studies. As I mentioned before, nerve conduction studies are part of neurological measurement where we are trying to test the peripheral nervous system. Okay, so let's say you have a person come with a clinical presentation of either motor or sensory loss in certain parts of the body. Okay, so for example, this person says, well, I can't feel anything in a part of my hand. Okay, or probably he says, I can't move my thumb very well. Okay, or maybe there is some loss somewhere. Now this can happen because of various reasons, right? You can have one nerve which is damaged because of some reasons. You could have a problem at the spinal cord level. You could have a problem at the brain level. Okay, or you could have, for example, you could have a nerve and a part of the nerve that is um, not working very well for some reason, or you may have symmetrical problem on both sides of the body. So various kinds of problems. Okay, and let's not get into the clinical details here. So how do you know whether the problem is in the peripheral nervous system or the central nervous system? Okay, so you can do some diagnostic tests, and that's what we are going to discuss. Now, we've already talked about the fact that the periphery of the body is connected to the spinal cord using neurons, okay? And the voluntary motor control is done through the motor nervous system or the motor nerves, and the sensation is got through the sensory nerves, right? And so what we can do is, if you want to test the nerves, you could do, for example, one thing to test the motor nerves would be to do motor conduction studies. So in this case, what we are doing is we are stimulating the nerve at any point in the body, and we are recording EMG from the muscles. Okay, now what innervates the muscles are motor nerves, right? And if you're able to stimulate the motor nerves, you should be able to record a EMG. And that EMG is called a compound muscle action potential, because it is made up of a lot of motor units, and the muscle contracts and you're recording the muscle action potentials, the compound muscle action potentials. Okay, and it looks something like this. So one way of doing this test would be to, so let's say this is the nerve that is innervating the muscle here. Okay, so we record from this muscle, we put some EMG electrodes and we start recording EMG, and we stimulate the nerve at this point, at a proximal part and at a distal part, right? Because of stimulus 2, you would get compound muscle action potential like this. Because of stimulus 1, you will get an action potential like this, right? There is some latency here, so after the stimulus, you won't get the EMG immediately, but there would be some delay, which is latency 1, and a delay after stimulus 2 before the compound muscle action potential comes is latency 2. Right? If you want to find out whether the nerve is intact here or not, right? You could actually calculate the motor conduction velocity, isn't it? Which is going to be distance. What is the distance between this electrode and this electrode divided by these two latencies? So that would give you the time that the action potential took to travel from here to here, right? And then you can also do other kinds of studies. For example, you could look at the shape of this motor unit, this compound motor action potential, and you can get some information, but more on that later. Just like you can study motor nerves, you can also study sensory nerves. Now, how do we do that? One way of doing that is to stimulate them, let's say, some kind of sensors at here, for example, and then you could record from this part of the nerve, right? And when you do that, what you get is the sensory nerve action potential, right? Just like you have the compound muscle action potential. In that case, the muscle is being given the signal, given the action potentials from the nerve, and the muscle generates an action potential which we are recording. Here we are directly recording from the nerves, and therefore we say it's sensory nerve action potentials, or SNAP for short. So the idea is that you stimulate at some point of the nerve, and then you record from here. And you can, of course, you will get a sensory a nerve action potential, which would be, as you would imagine, much smaller in amplitude than the CMAP, but just because CMAPs are muscle signals and not nerve signals, right? And you could calculate, for example, the sensory conduction velocity. If you know this distance, if you know the latency, you can calculate the conduction velocity, right? So CMAPs and SNAPs give you ways in which you can test the integrity of the peripheral nervous system. Now, one of the things that you should note is that CMAPs are much larger than the nerve SNAPs, okay? One reason that is because muscles are much bigger than nerves, and they can generate much larger action potentials than nerves. And also, well, individual nerve fibers probably will generate the same amplitude, but there are many more muscle fibers than nerve fibers at one place. And therefore, the compound muscle action potential is going to be much larger, usually a few millivolts in size, while the SNAPs are going to be 10 microvolts or a few microvolts. Okay. Now let's just think through what kind of abnormalities these tests can detect. Now, one of the things that we've already looked at is that if there is a connection loss in the nerve, or if there's a transaction in the nerve is split or something of that kind, then you won't get the CMAPs and SNAPs, and you can detect that. But you can get more information than just that, okay? So we already talked about the fact that nerves can be fast or slow, right? They can be fast because they are bigger nerve fibers, and therefore the resistance is less, so the signals can travel much faster, or they can be slower, right? Now, depending on which nerves you are stimulating, there is going to be a speed difference between the traveling of action potentials in different nerves. So, for example, if you are stimulating far away from the recording site, then the fast nerve fibers have an action potential that comes like this, while the slow nerve fibers give an action potential here. So there's a kind of a dispersion, isn't it? And because of that, can you see the SNAP shape changes compared to this shape when you are stimulating closer to the recording electrodes? You can see the same thing in motor neurons as well. So if the recording is close enough, then you get a shape like this. If you have a recording that is far away, then you can see that the action potentials in the fast nerves are going to travel faster, and you will get a muscle action potential because of the fast nerves, and the slower will come after a little bit of time. And when you add them up, you get a slightly different shape. And so the shapes can also give you some information about the integrity of the peripheral nervous system. So let's take a look at some things that we can get from here. So let's say you have a motor neuron here. This is the muscle, and you're recording from the muscle, okay? And you're stimulating at two sites, S1 and S2. S2 is much closer to the muscle, while S1 is further away from the muscle. So in the normal case, the stimulus 1 and stimulus 2 should give you almost the same shape of the CMAP, right? Of course, the latency is going to be different, but the shape is going to be similar. Now, let's say there is axonal degeneration. That is, some of the axons have actually broken off. They are not there. Then what will happen? Stimulus 1 and stimulus 2 both are going to be smaller in amplitude than usual, but they are both going to look the same, right? Because whether you stimulate here or whether you stimulate here, the only axon that is going to carry action potentials to the muscle is this one. Let's say you have demyelination, which means that the speed of the action potentials traveling is going to change. Then what is going to happen is when you are stimulating close enough, the speed is not going to change much, so the stimulus is going to be almost the same shape as the normal shape. But when you're doing farther away, the signals are going to be spread out a little bit more. Different motor neurons will conduct at different speeds because they will have more or less demyelination, and therefore you have a different shape of a signal, and that can give you that information. Let's say you have a vascular lesion and the nerves have died out, then you don't get any signal, and then you know that there is a problem. So those are some of the ways in which you can use nerve conduction studies to figure out what the problems with the peripheral nervous system are.